Hey everyone. So picking up where we left off in the previous video, we said that we've already reviewed what the output of the match filter, what the equation looks like, the convolution in terms of its integral form, and we took a look at what S of t and what H of t, we reviewed what those terms were. And in this video, we are going to actually write S of t, which is our input signal, and H of t, which is the impulse response of the match filter. We're going to write them in unit step form. And actually, I think just in this video, we're going to try to find S of t in unit step form, and then I might have to do another video to detail how to actually find H of t from the graph of S of t, and then write it in unit step form. But to start, we look at S of t, and the best way to think about doing these in unit step form is by looking at the graph and seeing what functions actually are in this graph. And we can see that in this specific graph, for example, 1, that there are at least just two functions. We have the function y is equal to 0, where the signal level is equal to 0 from negative infinity, from time is equal to negative infinity all the way up until time is equal to 0. And then we also see that it's equal to 0 from time is equal to capital T all the way to infinity. So we also have another function, and that is this ramp that is ramping at a rate of a over t, and it's occurring in this time domain between 0 and capital T. So the way that we would write this in terms of unit steps would be, we are going to multiply this function. Anything that turns on, we multiply by a unit step and we add it into the equation. And then when that function turns off, we subtract it out of the equation at the time specified in terms of unit steps. So for example, this function, this ramp function, is actually equal to, it has a slope of a over capital T, and we multiply it by t. And the way that we would find that is by just finding the equation of a line. We would use the points 0, 0, and t, a. So that's how we found the slope. And if we plugged it into our y equals, our y minus y1 is equal to m times the quantity of x minus x1, then we would actually, instead of using x, we used t, we would find that that line, the equation of that line is equal to a over capital T times little t. And just to further detail just some of the variables that we're going through, is that capital T represents an actual instant of time in the graph. And oftentimes we use capital T for period, which would be the inverse of frequency. And this little t is actually just the time variable, and it represents just any, it represents the whole domain of time. So what we would do from here is then put this into unit step form, and we see that this function, this line, a over capital T times little t, it turns on at time t is equal to 0. And at time t is equal to 0, we have a unit step of u of t. So we multiply this function by that unit step, and we add it in. So, and then that function actually turns off because the function returns back to 0 at time t is equal to capital T. So we would multiply this function by the time at which it turns off, and we would subtract it out of the equation. So we would get a over t times little t, u of little t minus big T. And so if we were to factor this out, it might actually even look a little bit better. We would have a over capital T times little t, and just to make it look nice, open a bracket, and we would have u of t minus u of t minus capital T. Oh, I need to close the parentheses. And so now you can really see that this function is turning on at time t is equal to 0, and it's turning off at time t is equal to capital T. So that is how we would find the unit step form of S of t. In the next video, we will review how to find h of t, and we will do that by inspecting the graph of S of t, and then we will also write h of t in terms of unit steps.